Welcome to video clip 2.4, in which we discuss inclusive gateways and loops. So we again motivate this with an extension of our application scenario, which is as follows. So depending on the ordered product, materials from supplier A or supplier B, supplier 1 or supplier 2 may be sufficient to manufacture the product. In some cases, however, materials from both suppliers are required for manufacturing the product. So we have here the alternative: either supplier 1 is okay, supplier 2 is okay, or we need the material from both. We could model this situation using the exclusive OR split and also the AND split. The result you see on this slide. So how is that organized here? We have here the decision. The decision: either material from supplier 1 is required, or material from supplier 2 is required, or material from both suppliers are required, in which we have the two concurrent branches, which means requesting material from supplier 1, obtaining material from supplier 1, and concurrently the same for supplier 2. And then, let's say, the flow continues here. What we see here, yes, we can do that. We can represent this requirement as defined in the text, in the process model. But we have a little bit of increased complexity by this, and we have also a duplication of tasks. So certain tasks require or appear several times. So request material from supplier 1 2 times, obtain material from supplier 1 2 times, and also the same holds for the two activities of supplier 2. So we are seeking a way to express this in a bit more compact way. And inclusive gateways can be used to do that. So the inclusive gateway is also called the OR split, or join. That means any non-empty subset of outgoing sequence flow arcs is signaled depending on the conditions. And each condition that is evaluated to true signals an outgoing arc. It's also possible to have a default flow, and that is used only if all other conditions are false. Okay, here's an example. So the previous example now expressed using the inclusive gateway, in particular the OR split. And we see the OR split here. And here we we have one condition, that is material from supplier 1 is required. The other condition is material from supplier 2 is required. And then either the upper branch is taken, or the lower branch is taken, or both branches are taken. So we have the complete execution semantics we had in the previous process model here, represented in quite a compact way. The OR join synchronizes all incoming sequence flow arcs that can be signaled. So the OR join will be discussed in the next slide in a bit more detail, but in general it has the same task as the XOR join or as the parallel join, in the sense that there are many incoming branches, and I need to somehow synchronize all these and trigger the next activity only if all incoming flows from which I expect something to come, if everything or if all these branches have been signaled. All right, let's discuss that in a bit more detail. So we have a number of remarks on the OR join. So again, an abstract example. The OR join is the guy here on the right-hand side. This modeling construct provides a high degree of flexibility, so OR splits and OR joins as a construct. But the OR join has also non-local execution semantics. So what do we mean by non-local execution semantics? That means the join cannot decide locally whether to signal its outgoing edge or not. In all other constructs we had, the constructs could decide locally what to do. So the XOR split looks at the conditions and then locally evaluates which branches to take. The AND split just signals all outgoing arcs. Also the same holds for the XOR join. So any signaling or the signaling of any incoming arc would then trigger the signaling of the outgoing. And the end join, what does the end join do? Well, it waits for signals from each incoming sequence flow arc and then signals the outgoing arc. So all these, all the gateway nodes we have been looking at so far have a local behavior. They can decide locally. So why is the OR join unable to do that? So let's look at this example. Here it might be the case that conditions 1 and 2 are chosen. So this branch is chosen and this branch is chosen. So what should the OR join do at that point in time? Well, it could wait. Maybe D will be executed and maybe there is an incoming signal from this edge. But how long should the OR join wait to decide that? We cannot provide an upper bound. There can be any runtime of, let's say, D can take as long as it likes. And therefore, the OR join is unable to decide at which point the OR join should trigger the outgoing edge. However, there is, if we limit the expressiveness of the OR join or the structure of the process model with the OR join, we can actually provide a solution to this. And that is for block-structured OR joins. So block-structured OR joins are quite easy to handle using false token passing. So in block-structured OR joins, from the OR split to the OR join, so each outgoing edge, let's see if I can sketch that here. From each outgoing edge of the OR split, there is a path that, the only paths that lead to the OR join. So this one leads to the OR join, that one leads to the OR join, that one leads to the OR join, and that one leads to the OR join as well. So in this case, we have a block-structured model. And then we can use false token passing to support or to evaluate the OR join. Let's use the same example that we had before, in which case conditions 1 and 2 will be chosen, so these two branches will be signaled. But how about the others? So condition 3 is not taken and the lower branch is also not taken. In this case, it's called false token passing, so we have additional information that is signaled along the edges, but the activities that are on the edges are not executed, and that is why it's called false token passing. So here false token comes, here false token comes, here false token comes, here and here as well. And in this case, the OR join, well, what is the OR join? The OR join changes to some kind of end join, because I expect from every incoming arc, I expect a signal, either a normal, a true signal, or a false signal, or false token. And in that case, it's quite easy, and that works because all paths that go out from the OR join, from the OR split, will go into the OR join. And in this case, it's quite easy to do that. Arbitrarily structured OR joins are really complex and are still being discussed in the academic world. There's a very nice paper by Eckhard Kindler in 2004 that raised these questions. All right, let's continue with the application scenario. So the order is checked for correctness and completeness after it has been registered in the system. If the order details are not valid, an order update is requested, which needs to be registered in the IT system as well and checked again. And this is repeated until the order is valid. So we already, by reading this, we have the feeling that we now talk about repetitive behavior, that we talk about loops in process models. So loops are iteration that can be modeled with an exclusive gateway. The branching condition of the OR split acts as the loop condition. And the loop iterations require the creation of new activity instances. And there can be many activity instances for a given process activity in one process instance. All right, so let's first look at the example and then look at the creation of activity instances. So here we have the normal flow. So we receive the order, enter order details, check them for correctness, and then we have the XOR split. And here the XOR split is well evaluated. Of course, the conditions are evaluated. Here we have condition order is incorrect. So if the order is actually incorrect, then this branch is taken. We request an order update. We receive an order update, and then we iterate again. Now, we do this until the order is correct, in which case the default flow will be taken because order incorrect is false in this situation, and then we can leave this loop. This example shows that there are, or put it the other way around, so far all our process models had one activity instance for each activity that occurs in the process model. Here it's more, because in the second iteration of the loop I have the second, let's say, activity instance of enter order details and the second instance of check correctness of order. And in this case, I'd just like to mention that in each new iteration of the loop, new activity instances need to be initialized. And then, but then the activity, let's say, the state transition diagram of activity is still valid, but I need to initialize new activity instances with every new iteration of this loop. bpm also provides uncontrolled flow. We have already seen uncontrolled flow, and that is when we looked at just the normal sequence flow. Activities may have several incoming and several outgoing sequence flow arcs, and the signaling these arcs is determined by the so-called uncontrolled flow semantics. And uncontrolled flow semantics means each outgoing edge is signaled. So when an activity has multiple outgoing edges, all these outgoing edges are signaled. And related to the incoming edges, each incoming edge that is signaled executes the task. All right, so that's the semantics of the uncontrolled flow. And if I have normal sequences, that's perfectly what I expect. So when the previous guy is terminated, signals the edge, I change my state to running, execute it, signal the outgoing edge, do an uncontrolled flow to the next guy in the line. So that's all perfect behavior. However, if I have a structure like the one we see here on this slide, what is the execution behavior of that one? Well, first, and that is, there's no doubt, we need to execute activity A. After activity A is executed, all outgoing edges are signaled. So the edge to B is signaled, the edge to C is signaled, B is ready and can then go to running, and C is ready and can then go to running. So actually what we see here is an end split, right? So after A is executed, the two outgoing edges are signaled and there's an end split. Now what happens after B terminates? After B terminates, this edge is signaled. What happens to D? Well, D finds an incoming edge that is signaled, so D executes. So D is executed. At that point, C terminates, or a bit later, C terminates, that edge is signaled, and D, what happens? D is executed again. So D is executed 2 times in this process. Why? Because the join of the uncontrolled flow is actually an XOR join, and the split is an AND split. Also, the two structures look very similar here. They do have a different execution behavior, and that makes it, let's say, that often leads to quite some confusion. So uncontrolled flow might lead to confusion because the split has an AND semantics and the join has an OR semantics. So we come to the modeling guideline related to gateways. I like to propose to use gateways for splits and joins rather than activities. The motivation is that uncontrolled flow semantics are often difficult to comprehend, that each activity should have one incoming and one outgoing sequence flow edge, and that makes it very clear because then activities do not have a split and join behavior, and the concepts of splitting and the concepts of joining are then represented by a dedicated element, which is the gateway. There's always, or not always, there are sometimes exceptions to rules, and here there's an exception that if we have a loop like this, then we can save the XOR join node in the beginning, and we can just model, we can model this by the two incoming edges. So either or enter order details can be started after receive order, but it can also be started after receiving an update. So here, no confusion is possible in this type of structure, so we could use it here. But in general, it's a good idea to have each activity has one incoming edge and one outgoing edge. The second advice and second modeling guideline in this context is avoiding mixed gateways. So BPMN allows mixed gateways. So what are mixed gateways? Mixed gateways are gateways that are at the same time split, that at the same time have a split behavior and a join behavior. So gateways that have several incoming edges and several outgoing edges. All right, so I'll try to sketch a process model with a mixed gateway and do this as followed. So when the process starts, executes an A, also an abstract example. After the A, we have an AND split. So parallel split goes this activity, and this activity is executed. So call it B and C. You can read it. Then we need to join the concurrent execution of B and C. And then we have here the mixed gateway, and there's a D and an E. And of course, these two also need to be joined. And afterwards, the process continues in some way. So the mixed gateway, of course, is the one in the middle that has several incoming edges and several outgoing edges. So now assume we, during the review of the process, we find that, well, D and E should not be executed concurrently, but D and E should be executed alternatively, either D or E. So, well, we can easily do that. I try to use the eraser now to change that. Well, that should not be an AND split, and that should not be an AND join, but that should be an XOR split. Oh, sorry. That should be an, need to erase it again. That should be an XOR split, and that should be an XOR join. So, wonderful. So we made sure that either D or E is being executed. But what happens by that? By changing of this, of the behavior of this gateway, we also affect the first part of the process in the sense that, in this case, B and C are executed concurrently, and each of them, B and C, both trigger the gateway. So the last part, so this part of the process is executed actually twice. The first time after B completes, and the second time after C completes. So we have two, we can have two, let's say, executions of D, two executions of E, or one of both. So, and that, of course, is undesired behavior. If the change is the other way around, if I change the first end to an XOR, then we have a deadlock situation. So we have a behavior mismatch, or let's say a behavior that we do not desire in our process model. So it's a good idea to avoid mixed gateways. And in the first case, well, we just can have one a gateway, the AND gateway, and then we have, well, that's the join gateway. And then we have a split gateway, and that, of course, can be also, and by, let's say, by using two gateway symbols and attaching them with sequence flow, we have the same behavior, but we have, for each concept that we have in our process model, we have one element that represents it. So one concept for joining and one concept for splitting, and these are represented by two different symbols in the process model. It's always good to represent one concept that from the original, from the domain I like to represent, by one element in the model. That concludes video clip 2.4, in which we discussed inclusive gateways and loops. So we discussed the split and join behavior of the OR gateway, especially the OR join. We spent some time discussing this. We have seen that we can use loops, or we can use XOR splits to express loops. We discussed uncontrolled flow, or the problems that are related to uncontrolled flow, and we ended with modeling guidelines related to gateways, especially related to mixed gateways.